Okay, we're back talking about exponential applications, exponential growth and decay. And here's an example of a radioisotope with a half-life, carbon-15, has a half-life of about 2.5 seconds. And so what that means is if I had a chunk of this stuff made of carbon-15, however much I had in the first place, in 2.5 seconds, half of it's going to be gone. Okay, and where did it go? It radiated away. And hopefully you're not standing too close, or maybe you're wearing a protective suit, who knows. But so that's kind of what half-life is talking about. So let me just make up an amount for this example that we start with. For simplicity, let's just say we have 100 grams, it doesn't really matter, kilograms, whatever you want, let's say grams, 100 grams of carbon-15, and 2.5 seconds later, half of it's gone. So now we're down to 50. 2.5 seconds after that, half of that's gone. Now we're down to 25. 2.5 seconds after that, half of that's gone. So now we're down to 12.5, and then in another 2.5 seconds, we're down to 6.25, which maybe I should round to 6.3 just to restrict my accuracy there to 1 decimal place, but that's okay. You'll get the picture. Let me just leave that as it is and see what it looks like graphically. So let's go ahead and put our standard XY graph. And I'm going to write in here grams just to remind myself I was talking about a number of grams. And over here for the X, I'm going to put seconds under that to remind myself I'm talking about seconds. And oftentimes you'll see these graphs written in T for time, because it's talking about time. That makes sense. And up here maybe A instead of Y, A for the amount after a certain time. So let's go ahead and try to find the functional form, and we'll also put these values on the graph. Let me go ahead and put the values on the graph and then try to find the functional form. Well, if I want to include everything in the domain here, shown in the X values, I've got to go from 0 to 10. So let's just put 10 little hash marks. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that wasn't exactly extremely accurate, but that's okay. 1 to 10, I'm going by ones over here. Well, as you notice on the y-axis, our range is pretty large relative to the x-axis. And that's what happens with these exponential models of growth and decay. The top value is 100, the bottom value is 6.25, so let me just make sure we go up to 100. I'll count by tens. How about that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 10 is 100. Okay, so this time I'm going by tens. 30, 40, 50, 60, 70, 80, 90, 100. Is it okay that I have a different scale here? Yeah, it's okay as long as you have a well-defined system here that you're using for your numbers for the x values and your numbers for the y values. So this one I'm going by ones, this one I'm going by tens. That's a perfectly acceptable and well-defined way to put it. So, all right, if x is 0, I want to put the points on the graph. Y is 100. If x is 2.5, y is 50. Okay, so here's 2.5 matched up with 50. It's about right there. If x is 5, so 5 seconds, I've got 25 grams left. 7.5 seconds, I've got 12.5, so I don't know, about right there. And 10 seconds, I've got 6.25, so maybe kind of about right there. And you can see the trend here and what the graph looks like. And let me just try to connect this with a smooth curve. Something like that. Okay, a little hard to do by hand. And that just kind of keeps going off to 0. You could go with the negative x values and you get something that looks like this. Coming down this way, and so there is exponential decay, and what we see here is simply a very rapid decay. I mean, this scale is huge compared to this scale, so each one of those steps is a very big decay. Just like we saw exponential growth had very large steps of growth, this has very large steps of decay. But what is the functional form exactly? Let's try to determine that. Y equals a b to the x. What's a, what's b is essentially the question. So here's my exponential form, a times b to the x. And this says that b is a fraction will give us exponential decay. Let's just see if we end up with a fraction for b to test that definition. So the first value is a nice one to go with to start to try to find your a and your b. That is when x is 0, because anything to the 0 power is 1. So that's a simple thing to do. Let's put 100 in for the y, equals a times b to the 0 power. There's the x value. B to the 0 power is 1, so this must be equal to a. So far then, I've got y is equal to 100 times b to the x. Now, how do I find the b? Just stick in some other point, some other information that we have. How about this guy? Pick one with a nice round number there, 5. This would give me y equals 100 times b to the 5th power. And I don't want my y there. I want to plug in the y value of 25 to match with my x value, and then go from there to find b. So let's divide both sides by 100. Okay. So that gives me 0.25 is equal to b to the 5th power. I left a little space there on purpose because if I want to get b by itself, I'm going to have to take the 5th root. Okay, and I'll do that to this side as well, the 5th root. The 5th root of 0.25. If you want a whole lot of accuracy in your functional form, then you want to leave it something like that. But I'm going to go ahead and estimate it. So this is the 5th root of 0.25, or 0.25 to the 1/5 power, or 0.25 to the 0.2. That's all the same. This gives me b is about 0.758. 758. So that altogether, my functional form is y is approximately equal to, I'm saying approximately because I approximated this, 100, and I'll use parentheses here for my times, 0.758 to the x. And there's the functional form that models that data pretty well. And indeed, b came out as a fraction, like we were saying here. Now, there are other ways to get exponential decays functionally with negative exponents, for example. So stay tuned. I'll talk more about that in the coming videos.